Now, today I will discuss the general penalty or barrier function method for those nonlinear programming problem where we are having inequality constraints as well as the equality constraint. Not only that, we will solve a problem, I will try to solve a problem for the maximization type of nonlinear programming. Now, I will start the class with this example today. Now, this example I was just mentioning in the previous class, and hope you have done the solution of it. Let me just do the solution for this and you just check it whether you have done the correct one or not. Now, we have to minimize our ckx. We are solving through the interior penalty function method. This is equal to x1 minus 2 x2. Now, you see the constraint has been given in the form of greater than equal to. That is why I will make it as less than is equal to x2 square plus x1 minus x1 minus 1 less than is equal to 0 and minus x2 less than is equal to 0. All right. Now, we are having the barrier constant, that is say C k, and the summation will be there. That is why I will consider ln minus this function. That is why the function will be the original function minus ln x2. All right. Now, this is equal to 0. The first order necessary condition gives you the condition that x1 minus c k divided by, for this case, plus x1 minus x2 square equal to 0, and we are getting another condition by partially differentiating with respect to x2, that is minus 2 minus ck divided by 1 plus x1 minus x2 square, and for this one minus 2 x2, that is why this is plus 2 ck minus ck divided by x2 again equal to 0. We are having two conditions together. All right. This is equal to minus 2 plus 2 ck x2 1 divided by this one is equal to 0. This is not x1, this is 1 minus, certainly this is 1 minus this one. All right. Now, from this condition, from here we are getting that ck is equal to 1 plus x1 minus x2 square. All right. If we substitute this value here, we are getting one equation, that is x2 square minus x2 minus ck by 2 is equal to 0. All right. And from here we are getting two values for x2. Actually, this is one is x2. We are getting two values of x2. One will be within the feasible region, another one will not be feasible region. We are having this one within the feasible region. You just check for the minus, it is not within the feasible region. All right. If this is my x2, then we can substitute this value and we will get x1 is equal to 3 ck plus 1 plus 2 ck minus 1 divided by 2. All right. If we get these two values for x1 and x2, then what we will do, we will formulate the table for different values of ck, x1, x2, the value of r, the value of f. All right. One thing we can do, we can make ck tending to 0. We will get the values for optimal value for x1 and x2. This is one way we can get it. Otherwise, we can, if we just substitute ck tending to 0, this term will be 0, this will be 0, and we are getting 1 minus 1 divided by 2, then we will get this value equal to 0, and for x2 star we will get ck tending to 0, that is why 1 plus 1 divided by 2 x2 will be is equal to 1. Instead of that, if you consider different values of x1, x2 and c starting from 10, if we just get the value, we will see the value for x1 would be 16.79. If we substitute the value for ck here, then you will get the value for x1 this one, and for x2 you will get 2.79. all right. Need to ask what. Then for the r, the value will be minus 22.082, and the original value of f would be 11.21. Is it clear? How to get this value? This value we will get ck, if you substitute the value for ck here, x1 will come this, x2 will come from here, and the r value will come if I just substitute the value for x1 and x2 and ck here, and f value, the original f will be, that is x1 minus 2 x2 will be this one. Okay. If we just do for other values, then c 0.5, 0.1, 0.01, any problem? If ck tending to 0, this is 1 plus 1 divided by 2, that is 1. ck tending to 0, this is 0. Okay. And we will get a sequence of this, that would be 957, 1.207, like that. If I just summarize everything here, then we will get the value as this one. For different value of mu, just to see this is converging, x1 is converging here 0, x2 is converging to 1, and r value is converging to minus 2, and the f value is converging to minus 2. Okay. Now, this is the solution of the problem. One thing you must have observed, that this is one way the theorem is there for the interior penalty function method. If the function is considered, the unconstrained problem is being considered in this way, then if ck tending to 0, xk, rather the optimal solution will converge to the optimal solution of the original problem. Then, but it is again I need to mention that for this in general, if the constraint is being satisfied critically, then we won't get the optimal solution, the problem will be unbounded. Now, let us continue with the general model. General model is that whatever I said, that has been summarized here. Now, for the general model, where we are considering both the equality constraint as well as the inequality constraint, we are having a set of p equality constraints and we are having m number of inequality constraints. Minimization of fx subject to p plus m number of constraints. How to handle it? Now, we know for the inequality constraint, we are having the interior penalty function method and the exterior penalty function method. Now, for the constraints of the type equality type, can you guess what could be the penalty, how the penalty will be calculated? We expect that for the optimal x, the equality constraint must be satisfied equally. That means, for the corresponding x, hkx must be equal to 0. But if the solution is not optimal, then we will see that if the solution is not optimal, then hkx will not be equal to 0, it will be some other value. Okay, that value will be the penalty value. That is why this value can be negative, this value can be positive. To make it just like our exterior penalty function method, we can take one penalty function as maximum of 0 and hk square. If this is so, then we can have the unconstrained problem like this: minimization of fx plus summation ck hk square plus cj prime. This we are considering less than is equal to, we are considering the exterior penalty function method. We can consider the interior function as well here. Now, this is the problem. Now, you see there are two functions. What is the property of these two functions? This function will be 0 if it is in the on the constraint, and if it is non-zero if it is not on the constraint, because this is equality type of constraint. And for inequality type of constraint, this will be 0 if x is not within the feasible region. That means x is not satisfied with all the inequality constraints. That is why if we just summarize, then we can say that here the terms ck hk square can determine the penalty incurred by the equality constraint for selection of a particular x, and for optimal x certainly hkx is close to 0. Thus, for large value of ck no penalty is generated. Now, for the we are making ck tending to infinity. That is why we have considered the exterior penalty function method, where we are making cj prime tending to infinity as well. That is why here also this is the penalty term incurred, and if x is the feasible within the feasible space, then gjx is the corresponding penalty, otherwise no penalty is incurred. Okay. Now, that is why we can say that one function is a function of hk and another one is a function of gj. One is, if we say one as a psi j and phi j and another one as a psi j, then we can say that a phi j is equal to 0 for hkx. Equality type of constraints, hkx is equal to 0 and this is equal to 0. And if hkx not equal to 0, then phi of j will be greater than 0. Why it is greater than 0? Because we have considered phi as square of hk, that is whatever violation of constraint is there in the positive side or negative side, we are considering the square of it, always it will be positive. Okay. And the psi j again will be positive, because gjx we are considering in general case less than is equal to 0 type. That is why always psi will be positive when x is not within the feasible space. To make the same type phi and psi, we considered hk as hk square. If this is so, then we can also consider psi as the inverse barrier function. We can consider the logarithm function just like previous. This is a general model. Okay. And for the exterior penalty function method, we can have 0 gjx, we can have max of 0 gjx square, we can have max of 0 mod gjx, alright. That also we can consider, or we can consider to the power p, where p is a positive integer. That is a general model for us, and this is the in general the interior penalty function method. The algorithm already I have discussed. And for the exterior penalty function method algorithm already I have discussed. The only difference is that here the c values are increasing, whereas for the interior penalty function method c value is decreasing, then only we can approach to the feasible region. That is the difference. Now, if we have this type of example with us, how to solve it? Okay. that x1 to the power 4 minus 2 x1 square, you see one constraint is of equality type and another constraint is of inequality type. Okay. Let me consider now how to get the unconstrained problem. Whatever problem we dealt till now, that we were not having any equality type of constraints, but here we are having equality type of constraint. Here H is of equality type, and that is why once we are considering the unconstrained problem, we will have hk square as the penalty function. Along with the penalty parameter we will consider, and here we will take maximum of 0 and this, alright. That is why we will have the function this way. RH is the parameter we have considered for the equality type, this parameter is the penalty parameter, and here RG is for the inequality type, this is the penalty parameter. We did not consider max of these because we have considered those combinations of x1, x2 which are outside the feasible space, because this is the extension of the exterior penalty function method. That is why the value will not be 0. Here the value will be gx square, alright. Now, if in this case if we consider different value of R H and RG, by considering the first order necessary condition, we can have a series of values equal to 0. Then you see this table is converging to x1 as 0.99 and x2 as 1, whereas the objective functional value is converging to 2.99. Okay. Otherwise, from the first order condition, if you just consider the RH tending to infinity or RG tending to infinity, you will get the same value, alright. Let me consider another problem that is of maximization type. See, the problem is plus 16 x2 subject to, this is a maximization type of problem. The constraints are x1 plus x2 less than is equal to 5, x1 less than is equal to 3, x1 and x2 greater than equal to 0. Now, we want to apply the interior penalty function method for this, and we will consider inverse barrier function for this. That is why the R ck x will be is equal to minus x1 square minus 4x2 square plus 8x1 plus 16x2. Now, this is fx and the function will be minus say c k divided by x1 plus x2 minus 5, okay, minus ck divided by x1 minus 3. One thing I must say that you see here the constraint is of less than equal to type. We have to make the constraint of type greater than equal to, because this is a maximization problem, alright. That is why the greater than type of equation, that would be 5 minus x1 minus x2. Here it will be 3 minus x1. That is why this value will come as plus, alright. 5, no, let me write down with the proper form. If I just write down with the proper way, then ck divided by 5 minus x1 minus x2. All right. If you want to make it is less than equal to type, if you want to remain in this way, then you have to take the barrier function as positive value plus ck divided by that one. Otherwise, you have to take this way, minus ck divided by 3 minus x1 plus minus ck divided by x1 minus ck divided by x2 from 4 constraints. All right. Now, this is one unconstrained optimization problem. You find out the value of grad of r is equal to 0. If we equate, we will get a relation between x1, x2 and ck, and for different value of ck, if we just substitute, we will get the values, and we are starting from the point 1 1, that is why ck we are considering as 1 as the first iteration, k is equal to 1. We are considering ck equal to 1, we will get x1 as 2.31, x2 as 1.85, r as 25.44 and the f as 29.054. Similarly, if we just go to the next iteration, r is equal to 2, and by considering ck tending to 0, it will be, that is why ck will be this one, 2.75, 1.9, 29.62 and 30.398. If we just do all the iterations for different values, the lower value of this one, we will get that this will be 3.00, 1.97, 30.99 and 30.996. You see, both the values are almost same. If we just extend it further, just do it, try, this will again come, it will converge here. Okay. This way we can solve the exterior penalty, we can solve the problem with the interior penalty function method. Now, what I suggest that you consider another problem to solve, that is maximization of x1 to the power 4 minus 3x1 x2 cube plus x3 cube. There are 3 variables together and the constraints are subject to x1 minus x2 square less than is equal to 18, x1 greater than equal to 0, x2 greater than equal to 0. Okay. And there is another constraint as well, that is x3 square minus x1 less than is equal to 25. Okay. Solve this problem and get the optimal solution for this. Thank you for today.